Okay, so section 2 deals with sets. Okay, so at the end of this section, you should be able to use set language and structure as applied to elementary mathematics. You'll see the connections between finite sets and whole numbers. And you should be able to see also what it means to have a one-to-one correspondence. Okay, so in the years from 1871 to 1884, George Cantor created set theory, which has a profound effect on research and mathematical teaching. Sets and relations between sets are a basis for teaching children the concept of a whole number and the concept of less than, as well as addition, subtraction, multiplication of whole numbers. Okay. Remember, these PowerPoints are available to you through Blackboard. So a set is any group or collection of objects. The objects that belong to a set are called elements or members of the set. One method of denoting a set is to simply use the elements inside braces. So remember, these are the curly brackets. These are the ones that I always have very difficult time writing myself, especially the one on the right. So you use a capital letter, must be capitalized, and then equals to curly brackets, and then you list your members. It could be numbers, it could be names, it could be words, it could be pictures, it could be really anything. Okay. So each element of the set is listed only once. Even if you have it appears twice, you only write it down once. The order of the elements is not important. And the symbol that we use to say that an element belongs to a set, it looks like an E, right? And then it's just saying this belongs to the set, and then you would write the set. If it doesn't belong to it, then it's this E looking kind of symbol with a slash through it to indicate that the element does not belong to the set. Okay, so and we should be seeing some examples. Let me see. I'm trying to see if there's an example down the line, but if there isn't, let me show you real quick. Hold on. Let me clear this. Okay, so for example, if you say 5 belongs to the whole numbers or 5 belongs to the integers, you would say 5, and then it would be this, and then the symbol for the integers looks something like this, kind of like a double I, sort of, right? Something like that. Or 1/2 belongs to the, or doesn't belong, right, in the integers. Or is it the, I'm sorry, I think this is the integer. Sorry, that's not the symbol. It's this one with the double. Right, so 1/2, that's the symbol for integers. This 1/2 actually belongs to the rational numbers. And I believe that's a Q looking kind of symbol. Okay? The symbol is not that important. You could just, say even this, something like this, and say, well, it belongs in here, which would be kind of obvious, right? If you see it, that it's in there, it's in there for sure. All right, so that would be something like that. So this just means that it belongs to, I guess, the set belongs to this. Okay. Okay, so that is, and so now, and then we can say if a set should be, if we're going to call it a set, must be well defined. So what that means is basically you set up the parameters to tell us whether or not an object or an element actually belongs in the set, and it should be easy to see or easy to calculate if it belongs in there or not. Okay, so one example that it says in the book, I believe, said something about all the people that live in California that ate rice on Friday. So is it possible? Definitely not feasible, not easy, but could you find all those people that ate rice in California on a Friday? and you should be able to, right? It technically would be possible to do that. It just would take a long time, and you'd have to know specifically which writing. But it would be so something well defined. Again, you give the parameters for it, and it's something that it's there's no gray area. It's either yes or no, right? So methods of describing sets. So the listing method or the roster method is basically just listing them out. So for example, C equals red, green, yellow, blue, and you can assume that C means colors. N is for the natural numbers, and you can start 1, 2, 3, 4, dot, dot, dot. Now these ellipses mean that you go on forever, right? It continues, and you can see that with the pattern that was set up beforehand. So you know it's going to be 5, 4, 5, 6, 7, 8, 9, 10, and so on. For this one, L for letters, lowercase letters, A, B, C, D, and then you can assume that it's E, F, G, H, I, J, K, all the way down to Z, lowercase z. Okay. So this is listing method. So you have to see the pattern to be able to determine the rest of the whatever's elements are in the set, right? Or it's finite. This one does not have ellipses, so you know it stops there. There's only 4, right? Now another way to do it is to describe. All right, describe the set, and this is called set builder notation. So you don't necessarily list them out, but you're giving the parameters as to what belongs in that set. So here we're naming the set E, and it says, so E is equal to X. This vertical line means such that X, again, this means belongs to or is an element of, N is the natural set of numbers, and, so you can put more than one parameter, so and X is also less than 11. So 11 would not be in there, right? So if I were to write those numbers out, right, it would be the set of natural numbers. So I'm starting off with 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I would stop at 10 because 11 again would not be part of that set. All right, so which of the following sets, write the following sets using builder notation. So for builder notation, again, you need to, and it already gives you the answers here because I'm not in presentation mode, but I could always switch over, right? Let's see. Yeah, I don't think I want to do that. Okay, anyways. So for this first set, you got to look at the pattern and see what is it going. I mean, you could follow the pattern and you can tell me, okay, it's going to be even numbers. So 12, 13, 12, 14, 16, sorry, 12, 14, 16, 18, and so on. So then this is going to be the set builder notation. So again, set builder notation just sets the parameters. So it's going to be X such that X is, and what is X? X is an even natural number, right? Or you could also say that X such that X is 2 times N when N is a natural number. So right, so you're plugging in the natural numbers. 1, if I plug it in here, I get 2. If I plug in 2, I get 4. If I plug in 3, I get 6. If I plug in 4, I get 8, and so on. So that's one way to build that one. So this is what we usually use to signify what the even number is. It's 2n when n is a natural number, and you just count off 1, 2, 3, 4 and plug that into the 2n, and that'll give you even numbers. For the odd numbers, it's you start off with the 2n, but you got to subtract 1 so you become even, right? So if I plug in 1, I get 2 times 1 is 2, and then minus 1 gives me the 1, and so on. So this one says X such that, and it's always such that, and then that same variable again, X is an odd natural number. So we should know what odd natural numbers are. And then this is the other way to write it again, X such that X is equal to 2n minus 1, where n is a set of it belongs to the natural numbers. So 1, 2, 3, 4, and so on. You're plugging in those numbers in there. Okay, now write a set A equals to 2k plus 1 such that k is equal to 3, 4, 5, and 3, 4, 5. So it's not that long. by listing its elements. So basically we're listing making the table k is 3, 4, 5, and then we're plugging in that into the 2k plus 1, and it gives us the elements 7, 9, and 11. So that's our answer, 7, 9, 11. So this is basically telling us what to do, right? Plug it in there, and these are the numbers you're plugging in. Okay, so this one says, write the set b equals to x such that x is a positive even natural number less than 8. So again, you got to follow the rules here. Positive, even, natural number. So positive, of course, we're starting out with 0. Even natural number. So we start with 2, 4, 6, and it has to be less than 8, so you would stop there. Okay. Now, two sets are equal if and only if they contain the same elements. So they have to have the same elements, so they're going to have the same amount of elements, and it's going to be basically a copy of it. Every single element that is A has to be in B. So if a set A is equal to a set B, we write A is equal to B. If A is equal to B, then every element of A is contained in B, and every element of B is contained in A. So if you were to prove this, if you had to prove that a set was equal to another set, that's what you'd have to prove. You'd have to prove that set A, everything in A is in B, and then everything in B is in A, and there's nothing left out. If A is not equal to B, then there's at least one element that is in A that is not in B, or vice versa, right? Now, a one-to-one correspondence means basically that you can pair it up from one to another. So if the elements of sets P and S can be paired so that for each element P there's exactly one element S, and for each element S there is exactly one element P, then the two sets are showing a one-to-one correspondence. All right, so it looks something like this. Now, this idea of one-to-one correspondence might seem simple in elementary, but this is the basis for functions when we get to algebra and those kind of things. Remember, for functions, one input gives you one output. So this is where we're getting at, and you're kind of laying the groundwork for the work they're going to do later on as far as functions. So if they understand this very well in elementary, once they get to algebra, it's going to be very simple. So the set 1, 2, 3 can be placed in a one-to-one correspondence with set ABC. They each have 3 elements, and we're just saying 1 goes to A, 2 goes to B, and 3 goes to C. These are not the only possible pairs to establish the one-to-one correspondence. Of course, you could do a bunch of different possibilities. You can say 1 goes to B, 2 goes to A, and 3 goes to C, or 3 goes to A, 2 goes to C, and 1 goes to B. You can do any kind of combination, but the more, I guess, logical and best way to kind of just write it is to use 1, 2, 3. You're basically counting these off, right? So another way to illustrate this is to use a table or even a tree to show the different combinations, how many combinations you can get. So you can say A, B, and then C, the different possibilities. So in this order, A, B, C, or C, B, A. Then what if B is the first one? Then it's BAC, BCA. So this is basically just giving you creating a tree right on this right side to show the different possibilities. So how many different possibilities? We have 6, and then we're gonna get into that once we start counting how many different possibilities are for certain things. All right. So how can we determine the number of one-to-one correspondences between two sets? In our example, given the element 1 in the first set, there are 3 possible elements in the second set, which can be paired with the 1, namely A, B, or C. So this is just saying if on the first one it's an A, then they're just talking about how we set this up. So if you choose A to go with the 1, then you can choose either B to go with the 2 or C to go with the 2. And if B goes with 2, then 3 goes with the C. And if C goes with the 2, then the B goes. You got to switch it up, right? Then what if B goes in the first position? Then you got to switch it up, A or C for the second one. And if you choose A, then the third one has to be C. If you choose C as the second one, then the third one has to be A, and so on the last possible combination there. So there's 6. So if M can occur in M ways, and after it has occurred, event N can occur in N ways, then event M is followed by event n can occur in m times n ways. Okay, so let me just describe this real quick. What are they trying to say here? So what we're trying to say is this, right? How many possibilities? So, and you've seen this example, it's sort of like when they ask you, you have 3 pairs of jeans, right? So jeans, you have 3 pairs of jeans. You have a blue, red, and green. And then shirts, you have let's see, a white and I don't know, what's a different color? Pink. I don't know. So how many different combinations can we get? How many outfits can I get from this? All right. So we start off with the blue. So blue, then I can either wear a white shirt or a pink shirt, right? So right there, there's two combinations. Or I can wear my red pants with a white shirt or a pink shirt. That's another 2 combinations. Or I can wear my green pants and again white or pink. That's another 2 combinations. So in total, I have 6 combinations. Well, what's a faster way to count, to figure this out? Well, I got 3 types of jeans and 2 types of shirts. All I need to do is multiply, and that gives me 6, right? So that's all they're trying to tell us here. And this is called the fundamental counting principle, right? Fundamental counting principle. Okay. Now, again, equivalent sets, 2 sets, A and B, are equivalent, and we write it like this with a little kind of tilde A, tilde B. If there exists a one-to-one correspondence between the sets, recall if 2 sets are equal, they have the same elements. Equal sets are equivalent, but equivalent sets are not necessarily equal. So again, if they're equal, they have the same elements. But if they're equivalent, that does not mean that they are equal. That they don't have to have the same elements. They just have the same amount. They have a one-to-one correspondence. Okay? So, for example, let's say set A is equal to 1, 2, 3. And set B, and just like we said, order doesn't matter. 3, 2, 1, right? So are these 2 sets equal? Yeah, they have the same elements. Same elements. Okay? So is A equal to B? Yes, right? They're equal. Is A equivalent to B? Yes. So for this one, again, it's a one-to-one equivalent. One-to-one correspondence. So equivalence means that there's a one-to-one correspondence. So now if I did the same idea and I said A is equal to 4, 5, 6, and B is equal to 1, 2, 3, is A equal to B? No, it's not. Is A equivalent to B? Yes, it is, because you can do a one-to-one correspondence, right? I didn't really aim there, but you get the point. I'm sorry, I don't think you saw that. Let me go back. So again, if A is 1, 2, 3, and B is 3, 2, 1, again, the order didn't matter. Is A equal to B? Yes, they have the same elements. Is A equivalent to B? Yes, because they have a one-to-one. If I had 4, 5, 6 as A and B, it was 1, 2, 3. Are they equal? No, they're not equal. Are they equivalent? Yes, because they have a one. You can do a one-to-one correspondence. Okay. Okay, so here's a lot of examples. A is equal to PQRS, B is equal to ABC, C is equal to XYZ, and D is equal to BAC. Compares the sets. Each set is both equivalent and equal to itself, which is obvious. They're, you're comparing it to itself, so it has to be equal and it has to be equivalent to itself, right? A and B are not equivalent and are not equal. So this one are not equal. Obviously, they do not have the same sets, the same elements, and actually none of these have the same. Well, actually, no. There, B and D are the ones that are equal, right? So where's B and D? Right here. B and D are equal, and they are also going to be equivalent because they got the same number. They have a one-to-one correspondence, right? So they are equal. They both have ABC, and they both have 3 elements. So those are the only ones that are going to be equal and equivalent. B and C. So B and C, these are not equivalent. They are equivalent. Sorry, they both have 3 elements, but they're not equal. They don't have the same elements. Okay, so just you can kind of read the rest and make the same determination. Now, the cardinal number of a set is basically telling us how many elements are in the set. So here n, and we write n and then parentheses the name of the set inside equals to 5. So there's 5 elements here. There's 1. Here it's x such that x is this. So you actually have to figure out what this is. X is such that x is a real number where x is equal to x plus 1, and this is basically impossible, right? Like 5 cannot equal 6. So that's equal to 0. And this last one is called the empty set, and it doesn't say on here, but it's called the empty set. That's the symbol we use to show that it's empty, and that's equal also to 0 because it's empty. Right, now finite sets and infinite sets. Finite sets means the cardinality is equal to 0 or a natural number. So that means you can actually count the number of elements in the set. All right, so the number of presidents of the United States, we know how many there are. We're up to 45, I believe. For planets, we know how many planets there are, and of course it keeps changing. But as long as we follow the rules, we can figure out how many. There's infinite sets. So, for example, the whole numbers, when you see the ellipses, you can tell that's infinite. So we're never gonna know the end of that. And maybe a solution to equations such as x plus 1 is equal to x plus 1. So obviously any number you plug in will work. So that's an infinite set also. Okay. The universal set U is defined as that set consisting of all the elements under consideration. And then by under consideration, we're talking about by whatever could fit into the parameters you're setting. So we usually denote U for the universal set. So for example here, suppose that the universal set is defined as, and we just give some kind of definition for it, and it all depends on what you're using or what you're doing. So U is equal to X such that X is a member of the US Senate currently. Maybe you could have added currently just to be a little bit more specific. So denote the universal set with a large rectangle, and particular sets are indicated by geometric figures inside the rectangle. In this case, only members of the US Senate are included in the rectangle. This pictorial representation is a Venn diagram, so it would look something like this. So anything in this box has to be somebody that's a US Senator. So it would be a bunch of names, right? Then you could also do another set inside this universal set, right? So a subset. So f is equal to x such that x is a female US Senator. So everything in here would be female US Senators, and everything outside of it would be non-female US Senators. Now the complement of the set is sort of like negation. You're getting the opposite or stuff that's not in the set. So if I'm saying what is the complement of all female US Senators, well, it would be the opposite of everything that's outside of here, right? Not necessarily the opposite, but just what's not in here. Okay, so whatever's not in F, whatever's outside of F, that would be the complement. Okay, so you just gotta change it. And again, it's not the opposite, it's just whatever's not in here. Right? It might be the opposite if there's only 2 options. It all depends on how many options there are. But here it would just be anything that's not in here. Okay. The complement, again, this is written with a line above the A that denotes the complement of such a set. So here it's X such that X belongs in U. It's still in the universal set. So for example, in the last example, it said they're still a U.S. senator, but they don't belong to, maybe this would have been an F, right? So F complement is equal to X such that X or so somebody is a U.S. senator and they do not belong in the set of female senators. Okay. So here are some examples. If the universe is A, B, C, D, and B is equal to C, D. So again, B is part of this one, but not all of it. Then the complement of B is going to be the ones that are not in B. So it's going to be A and B. The complement of the universal set then is the empty set. Okay. So instead, U again is everything. So what is the opposite of everything? It's nothing. And then so nothing would be represented by the empty set. The opposite of the empty set again is the universal set. If U, the universal set, is an animal in the zoo, and S is a snake in the zoo, describe the complement of S. So it's any animal in the zoo that is not a snake. All right, and so here's another example. U is equal to N, and then E is equal to even numbers, and O is equal to odd numbers. Find the opposite, the complement of the evens and the complement of the odds. So obviously the complement of the evens are the odds. The complement of the odds are the evens. In this case, it's sort of like the opposite, right, of the one you're talking about, but it's what is not in the set. So brings us to subsets. And I mentioned that word before. So basically a subset is a set that belongs inside another set, right? So a set B is a subset of A such that B belongs, or is, sorry, that doesn't belong, but it's a subset of A. That means subset. If and only if every element of B is an element of A. When A is not a subset of another set B, we write A and then we write this subset symbol with a slash across it again. A is not a subset of B. All right, so the definition allows for B to be equal to A. Right, so B is a subset of A. So this implies that every element of B is an A. And then if you can do the reverse of that, so if A is a subset of B and B is a subset of A, then you're telling me that A is equal to B. Because if that's the case, then there's nothing missing from one set to the other. Okay? So again, if A is a subset of B and B is a subset of A, then it is equal to each other. And again, this is something that you would use to prove that one set was equal to another. You would have to show that A is a subset of B and then B is a subset of A. Then if that's true, then they're equal to each other. All right, so suppose B, here's a proper subset. So for a proper subset, suppose B is a subset of A and B is not equal to A. That's going to be a proper subset. So then there must be at least one element of A that is not in B. So we can say that B is a proper subset of A, and then this is the notation we use now without the little line underneath the subset. Okay, so here's an example. So we got A is equal to 1, 2, 3, 4, 5, B is equal to 1, 3, and P is equal to 2n minus 1, all x such that x is equal to 2n minus 1, where n is equal to 1. So again, we would plug in numbers to figure out the values that belong in here. So if I plug in 1, 2 to the first power is 2, minus 1 is 1. Plug in 2, 2 to the second power is 4, minus 1 is 3, and so on. Right here, 2 to the third power is 8, minus 1 is 7. 2 to the fourth is 16, minus 1 is 15, and so on. So you got 1, 3, 7, and 15. So B is a subset of P. So where's B? B is here, 1, 2, 1, 3. This one is a subset of P, 1, 3. Also, B is a subset of A, right? B is a subset of A. So 1, 3, you got 1, 3. A is a subset of itself, B is a subset of itself, and P is a subset of itself. So you could always say that. It doesn't lead you anywhere. You pretty much, you're saying A it has to be equal to B, right? Okay, now proper subsets. B is a proper subset of A because A has these other elements, 2, 4, and 5, that are not in B. Right? So B is a proper subset of A. So identify all the proper subset relationships that occur among these sets, and then B was also a subset of of P because it has 1 and 3 in it, and P has other elements other than that, right? More than that. Oops. So a little bit of an application, and I don't think we'll see much of this, but suppose A and B are finite sets. If A is equal to B, then the number, remember this means cardinality, and it means how many elements are in the set. So if A is equal to B, that means that the number of elements in A is equal to the number of elements in B, right? And they are equivalent also. So it is possible to establish a one-to-one correspondence between A and B. So I can kind of line them up and just make a line from one to the other. If A is a proper subset of B, right? So then if A has some elements that are in B, but B has more elements, right? So A doesn't have them all. Then A, the cardinality of A is going to be less than the cardinality of B. So there's going to be more elements in A than there are in B. Backwards. There's going to be more elements in B than there are in A. And it is possible to establish a one-to-one. It is not possible to establish a one-to-one correspondence because B is going to have more elements, and there's not going to be a way to do it, right? So you're going to be left with a situation where you might be able to do that, and then there's going to be extra elements on one of them other than the other. So then that's why it is a proper subset. Okay. And I think that's pretty much it. This you can read over if you want, but that's pretty much the basics of subsets or sets.